Chapter 4 is one of my favorite chapters of the whole year. In Chapter 4, we'll get into the different types of chemical reactions. So if you're in an AP Chem course, hopefully that's something that excites you. We need to start out with a little review of solutions. And you might remember the vocab terms solute, solvent. The solute is the substance that's being dissolved. It's often a solid, but it doesn't have to be. It could be a liquid or even a gas. The solvent is the substance that's doing the dissolving. It's often water. It could be anything else. Most of the solutions that we'll deal with are water-based. So when we look at types of solutions here in this video, we're going to assume that water is the solvent. You might also remember this rule of solutions that like dissolves like dissolves like. And when we say like, we mean that polar molecules can dissolve in polar solvents. Non-polar molecules can only dissolve in non-polar solvents. Okay, so this word polar, non-polar, that should be something that's relatively familiar to you, but you probably haven't thought about it for quite a while. So let's look at water, blast from the past. You might remember drawing water molecules, like Lewis structures of water molecules. We'd have the oxygen in the center. The oxygen has 6 valence electrons. They're organized as 2 pairs and 2 singles. And when we get into the bonding chapter, we'll look more at the specific angles and why the angles are the way they are. But you might remember drawing oxygen something like this, and then we'd hook on the hydrogens. Each hydrogen has 1 valence electron, and we kind of set it near the single electron of oxygen. And they'll share. This will be a covalent bond, so we'll kind of connect the dots. The hydrogens only need 2 electrons to fill the first energy level, so they're fine. Oxygen needs 8. He's got 4 electrons that are bonding electrons, and the other 4 are considered lone pairs. Now, you kind of might remember this shape as being bent. These electron pairs around the center oxygen are very important. There's actually 4 groups of negative electrons around the oxygen, and they all repel each other. It doesn't matter if the electrons are bonding electrons or lone pairs of electrons. They're all negative. They all repel. So the best way to get 4 groups of electrons as far apart as possible is kind of that tetrahedral shape. But in this case, 2 of the positions aren't really atoms. 2 of the spots are lone pairs. So what we're left with is a bench structure. And here it'll kind of note that the angles are approximately 105 degrees. Okay, so that might ring a bell from first year chem. Water is a bent molecule. You might also remember that bent molecules are polar. Polar molecules result when you don't have an even distribution of atoms around the outside of a particular molecule. Like in this case, I've got hydrogens, but they're not coming off at like 180 degree angles. It's this bent structure. These lone electron pairs are obviously negative. So we say this oxygen end of the molecule builds up kind of a partially negative charge. Not only are there, 4 electrons sitting on top of the oxygen, which obviously makes him negative, but oxygen has a really high electronegativity. Electronegativity being the ability to attract electrons. So even these electrons that are in the bonds are kind of drawn toward the oxygen. So there's no doubt that the oxygen end of a water molecule is partially negative. And that's kind of what they're showing here too. This goofy like squiggly symbol means partially negative. We're not going to say it's a full-blown -2 or 2-, because we're not transferring the electrons to oxygen. We're just not sharing them equally. They're drawn toward the oxygen, which means then that these poor little hydrogens are left partially positive. So we say that the water molecule is a polar molecule. It has an unequal distribution of atoms around the outside. Those hydrogens are not coming off at 180-degree angles. And most importantly, one end of the molecule is partially negative and one end of the molecule is partially positive. That's kind of the main thing I'm looking for in a polar molecule. There's opposite ends or opposite charges to a molecule. So if we say like dissolves like, and we know that water is a polar molecule, only other polar molecules will dissolve in water. That's kind of what this like dissolve like means. Now, on the flip side, if I had a nonpolar solvent, only other nonpolar molecules will dissolve in a nonpolar solvent. So we always use the example of water and oil. They don't mix. Well, water is polar, and oils and greases and fats are usually nonpolar molecules. So they won't mix or they won't dissolve in one another. So we need to know this. Water is polar. And that's going to kind of drive the solutions that we look at in this chapter. Another good example of a polar molecule is something ionic. Most ionic compounds dissolve really well in water. Now, there are some that don't, and we'll deal with that next semester. That'll be one of the last things we deal with. But if you think about it, like if I have sodium chloride, this is about as polar as it gets. We're completely transferring an electron from sodium to chlorine. So not only is the chlorine partially negative, but we usually say it's a full out -1. There's an extra electron on that chlorine ion. And then we say that the sodium ion has become +1. So ionic compounds are definitely polar molecules. One end is positive, one end is negative. So now let's say you throw a crystal of sodium chloride into water. A crystal of sodium chloride is just a repeating solid of sodium and chlorine ions, real organized, real tightly packed. Well, those water molecules are smart. And this arrangement is essential. We have to understand how this happens. The water molecules will surround a sodium ion. So this sodium ion came from the original crystal. The sodium ion is positive. Look at the arrangement of the water molecules. They'll arrange themselves so that the partially negative oxygen is attracted to the positive sodium. We call this a hydrated sodium ion, or sometimes they'll refer to this as a shell of hydration, where in solution you have all these ions, sodium ions, chlorine ions, and they become surrounded by water molecules. The arrangement of those water molecules is really important. On the AP test, they may ask you to draw a picture of a hydrated sodium ion. Or maybe it's multiple choice, and they would say, which of the following diagrams shows how sodium ions will dissolve in water? And what they're really getting at is this arrangement of the water molecules. If a sodium ion is positive, the water molecules will surround that positive ion with the oxygen end attracted to the sodium. And eventually, so many water molecules surround the ion that it really just kind of rips off the crystal structure. Opposite happens with chlorine. So now let's say I have a chlorine ion. The chlorine ion used to be part of this solid crystal. And now as it's in the water and the water molecules are attracted to this negative chlorine ion, check out the arrangement. Now around the negative chlorine ion, the water molecules arrange themselves hydrogen end attracted to the negative chlorine. The partially positive hydrogen end of the water molecule is attracted to the negative chlorine ion. And eventually, again, the chlorine ion just becomes so surrounded by these water molecules that it kind of rips off the crystal structure. The most important word that we should get out of this is right here. Dissociation. When an ionic compound dissolves in water, it dissociates into ions. Dissociate just kind of means to split. So if I had a beaker of salt water, it really exists as a bunch of hydrated, I won't draw the water molecules, Sodium and chlorine ions. Sodium, chlorine, sodium, chlorine. The ions separate from each other. And we say that solutions are very stable, unless I evaporate the water, obviously. But for the most part, if I have a solution of sodium chloride, the sodium chloride stays dissolved because those sodium and chlorine ions are never really in touch with each other. They're constantly moving and swimming around in the water, but they're surrounded by these shells of hydration, or these water molecules. It's kind of like little bumper cars or something, where the chlorine and the sodium will never come in direct contact with each other. So solutions are very stable. The ions will stay dissolved. Now, obviously, if I evaporate the water, then I lose the water molecules that are protecting each ion, and now those ions can collide, and if they do, they'll go back into the solid crystal structure. But we have to kind of think of this as a dissociation, and you might see these equations written. They'll call them dissociation equations. If I have sodium chloride aqueous, meaning it's dissolved in water, it's really sodium ions, I'll put a little AQ, and chlorine ions in the solution. They're +1 and -1. I'll put that in. +1, -1. It's not neutral sodium chloride molecules. There are no sodium chloride molecules anywhere in this beaker. They're all dissociated into positive and negative ions. And what we'll look at in a few minutes is the idea that, if I have these charged particles in the solution, they should conduct an electric current. If an ionic compound dissolves in water, it's a good conductor, or we say it's a strong electrolyte. So down at the bottom, when they bring up this word solubility, again, it varies between compounds, but in general, ionic compounds are highly soluble in water. They tend to be nice polar molecules, and we would often say that they dissociate 100%. 100% of the molecules dissociate to form ions. So we really don't have any neutral molecules. It's all charged ions. And again, there are some ionic compounds that don't dissolve well. They don't have a good ability to let go of each other, the positive and the negative ions. And we'll look at why that happens next semester. But if I say that something is slightly soluble, or maybe I say that it's not soluble, we mean that it does not dissociate in water. Water being the solvent that we'll use for 99% of our solutions in here. Now, there are other options here. We'd said that ionic compounds typically dissolve very well. They are polar molecules, and like dissolves like. There are some non-ionic compounds that also dissolve well in water. A good example is another polar molecule. Now, it could be polar covalent. So when we say a non-ionic compound can dissolve as water, it can dissolve in water as long as it can be attracted to the oxygen and the hydrogen ends of the water molecule. A good example of something non-ionic that does dissolve is a polar covalent molecule. And you may recall this word from first year chem. We'll again talk about polar covalent and all these polar molecules more when we do bonding. But this is a covalent molecule. We're sharing the electrons, but we don't have to share them equally. Again, it's kind of the situation that happens with water. We're sharing electrons, we're not transferring. But there's usually somebody that has a real high electronegativity, and the electrons tend to be held closer to that atom in the molecule. Kind of happens in this ethanol molecule. Ethanol and water are very soluble in one another. One end of the ethanol molecule is pretty non-polar. It's this guy over here. This end is kind of boring. It's got a carbon, it's surrounded by hydrogens. They're all evenly distributed around the carbon. Boring. Also, carbon and hydrogen have very similar electronegativities, so the electrons are shared kind of the same. But now you get over to this other carbon, and it's got some hydrogens, but then we've got this. We've got this OH group, this hydroxide group on the end of the other carbon. Oxygen and hydrogen have very different electronegativities, kind of like the water molecule, where the oxygen end is slightly negative, the hydrogen end is slightly positive because of those strong electronegativity differences. Oxygen has one of the highest electronegativities on the whole periodic table, meaning he really wants electrons, and he tends to tug on those electrons more than the hydrogen. Well, now let's say you put this ethanol molecule in water, and we had said the oxygen is a little negative, the hydrogen is a little positive. Same thing happens on a water molecule. The oxygen is slightly negative, the hydrogens are positive. Bingo! Attraction right here. Attraction. A non-ionic compound will dissolve in water as long as it can be highly attracted to those water molecules. And that's what happens here. That we've got this positive hydrogen on the end of the ethanol molecule, and it's attracted to the oxygen on the end of the water molecule.